Okay, we're starting into Unit 2 now, and Unit 2 is all about chemical bonding and the different types of chemical bonds. So the first section is going to go through and just talk about the three main types of chemical bonds in AP Chemistry. But before we can get into the types of chemical bonds, you guys have to understand electronegativity. You'll want to have a periodic table handy because we have to look at it to be able to figure out what's going on with these types of bonds. So we talked about electronegativity as one of our periodic trends. And by definition, it's the measure of the ability of an atom or a group of atoms, if we're talking about something with a polyatomic ion, to attract electrons. The thing that's attracting the electrons is the nucleus of that atom, is what it's attracting the electrons from another element. This trend is going to increase up the group and increase across a period. So when we're talking about electronegativity, we ignore the noble gases because the noble gases are not going to be involved in chemical bonding. And so if we're talking about increase up a group, increase across a period, then fluorine is the most electronegative element, and francium would be the least electronegative element. I would memorize that fluorine is the most electronegative element because it comes up a lot and it determines the types of bonds that are going to form. So there's three types of chemical bonds. There's ionic, covalent, and metallic. In this slide, we're going to talk about ionic and covalent. Ionic transfers electrons. There is no sharing. Covalent shares electrons, but there's two types of covalent bonds. There's nonpolar and polar. Polar means that they're not sharing the electrons equally. Nonpolar means they do share the electrons equally. A nonpolar covalent bond example would be any diatomic element. We talked about those in the last unit. So like oxygen is O2. That would be a nonpolar covalent bond. They share the electrons, but their electronegativity value is exactly the same, so they share them equally. Polar covalent means they do not share the electrons equally. In this case, there's going to be one of the elements has a larger electronegativity value, and it pulls the electrons closer to itself, and we're going to see that it creates partial charges here in a minute. And then the last type is metallic bonding. We'll talk about it on a different slide. It is really important to be able to distinguish what type of bond it has, especially when we're talking about nonpolar and polar, because that's going to play into our Unit 3 when we start talking about properties of different substances. It depends on what type of bond it has and how they're sharing those electrons. So if there's a really big difference between electronegativities, that's going to make your bond character be ionic. Bond character just means more likely is it going to be ionic or covalent. If there's a slight difference in electronegativity, then it's polar covalent. If there's no difference, then it's nonpolar covalent. So in your high school level chemistry class, you guys would have used the actual electronegativity values, which can be found on the internet or on periodic tables that are printed that have electronegativity values on them. But AP does not give you those values. So I do not want you to use the electronegativity values to figure this out. It's based on distance between those two elements on the periodic table. If they're really, really close to each other, they're probably covalent. If they're really far apart from each other, they're probably ionic. We're going to figure that out as we go through this set of notes. So an ionic bond is formed between a cation and an anion. The cations, as we've talked about in the last unit, are your metals. The anions are your nonmetals. Cations are going to be on the left side of the periodic table, and your anions are on the right side of the periodic table. If we're talking about an ionic bond, and this is going to come into play as we go through this unit, the larger the charges and the smaller the ions. Remember, we talked about Coulomb's law, and Coulomb's law is that math equation that relates the charge of your particles and the size or the radius of between the two bonds. So the bigger the difference in charges, or the smaller the ion, is going to increase that strength in the ionic bonds. So Coulomb's law still applies throughout the rest of the year and throughout this unit. Some characteristics about ionic compounds: they typically form crystals. You guys can think about sodium chloride as an example of an ionic compound because we're familiar with it. It has a cubic shape on its crystals. All of them form a little cube. And that's due to the ratios of positive to negative ions and the areas of attraction and repulsion within that ionic bond. They have high melting and boiling points because the ionic bond is so strong. They separate into ions when you dissolve it in water. So if I put sodium chloride into water, it separates into sodium and chlorine. They're good conductors of heat and electricity only when they're dissolved in water or when they're melted. So this is an example down here, the picture of showing what's happening in an ionic bond. We have sodium and chlorine. So sodium has 11 total electrons because it has 11 protons when it's in its neutral atom. And it has one valence electron. And again, we're using Bohr's model because it's easier to interpret than the quantum mechanical model. It has one valence electron out here. Chlorine has a total of 17 electrons, but there are only 7 in its valence shell. It needs 8. Sodium wants to get rid of its electrons so it can become like a noble gas. Chlorine wants to gain its electron so it can become like a noble gas. And so sodium is going to give chlorine its electron, and it becomes sodium positive 1. And now its electron configuration is going to match that of neon. And chlorine has accepted it and become chlorine negative 1, and its electron configuration is going to be like that of argon. That's the point of chemical bonding, is to get an electron configuration that is stable like the noble gases. So in an ionic bond, it is going to transfer an electron or electrons from the cation to the anion. The next one is covalent chemical bonds, which is also sometimes called molecular. It's formed between two nonmetals or sometimes a metalloid and a nonmetal. These are going to be the elements on the far right side of the periodic table. They can share 2, 4, or 6 electrons. We're going to talk more about that as we go through this unit. They have low melting and boiling points. Let's think about sugar as an example for this one. If I put sugar in a pan on a stove, it melts pretty quick. They're poor conductors because there are no true charges in a covalent bond. And if I dissolve sugar in water, it remains as a molecule. It's going to stay connected to each other whenever I put it into the water. It does not separate out like an ionic compound does. So if I look down here, this is showing an example of just 2 generic A and B covalent elements. So this one would be an example of a nonmetal. This could be a nonmetal or a metalloid. They do not transfer electrons. Like we saw in the last picture, they share them. So there's going to be an area where they share at least 2 electrons, and that stabilizes them. So now I have 2, 4, 6, 8, but this one also has 2, 4, 6, 8, and they're able to share those 2 electrons between them for stability. Last one is metallic bonding, and you may or may not have heard of this one in your high school level chemistry. Metallic bonding occurs between metal atoms. So like if I have a sheet of metal, like copper, or if I have iron or silver or gold, they do something weird where they are forming a bond. It is an attraction, but it is because it creates this weird thing called a sea of electrons. This can happen if it's just a metal or if it's an alloy where I have like bronze or brass, stainless steel, where I've mixed metals. And what happens is the positive nucleus are all there and they create a structure. And then they just sort of share all the valence electrons. They call it a sea of electrons. It's a delocalized sea of electrons. So delocalized means it's no longer connected to an individual atom of that metal. They just sort of share all the electrons. Because of this, they are able to shift around a lot more than your ionic and covalent compounds. So because they have that sea of electrons, that allows for the metal to be malleable. It can be hammered out into sheets but stay together because those electrons just shift around to wherever they need to. Same thing, it allows them to be ductile or drawn into a wire. They're good conductors of heat and electricity because those electrons are just all chilling out there for electricity to travel on. Then you have your positive nucleus. And then they're also very shiny. We'll come back to metallic bonding later in the chapter. Today we're really focusing mainly on ionic and covalent. So this is an example of your periodic table. And so over here, from lithium over to beryllium, all through the transition metals, and then all of these green elements all the way down here are all metals. These down here are our newest synthetic elements, and their properties are hard for us to know because they exist such a short amount of time before they radioactively decay that we don't really know exactly what their properties are. That's the reason these are grayed out. But we think if they were going to exist for a long time, that going down through here all the way over, these would all be metals. These are metalloids: boron, silicon, germanium, arsenic, antimonium, tellurium. They are metalloids. Everything to the right of those are our nonmetals, and hydrogen is a nonmetal. We need to know where the different elements are to be able to know what kind of bond they're going to form here in just a minute when we start looking at the types of bonds. So in AP Chemistry, we introduced this concept of bond polarity. This is going to be us trying to figure out what the type of bond is in a shared bond, a covalent bond. We have to figure out what the bond polarity is. And this is going to help us determine a lot of things later. So you want to get really comfortable with it now. So it is determined by a difference in electronegativity values. But remember, AP Chem is not going to give you the electronegativity values, so we can determine it with them, but we're going to use the distance on the periodic table to help us. So it says most of the time when you have these, you're going to see something called a partial charge. So I have a picture over here of hydrogen and fluorine bonding, and it has these weird symbols. That's called a partial charge. So in a polar covalent bond, the electrons are not being shared equally. So one of the elements is going to pull the electrons closer to itself. And when it does that, it takes on a partial negative charge. The other element is going to be partial positive. These are not ionic bonds. These are just not equal sharing of the electrons. And these have a huge role in the property of those compounds. And so the symbol they use is this lowercase Greek delta symbol. So the uppercase Greek delta symbol looks like a triangle. We use it a lot of times in science to say change in. This is the lowercase version of it. The element that is more electronegative is going to have a partial negative charge. The less electronegative element is going to be a partial positive. So let's go back to this slide and let's go ahead and add in our arrows to show electronegativity. So on this, we are going to show that if I move up, hold on, it is going to increase, and across is going to increase. So up and over, and then for electronegativity, we pretty much ignore this column. Now, going back to electron configuration, any of the noble gases that have a D block, so krypton, xenon, radon, can actually chemically bond. We can force these to chemically bond, but it is not effective because it takes more energy to force them to. And so we still just ignore them saying they can't chemically bond. Helium, neon, argon can never, ever, ever, ever bond because they don't have this expanded area of that D block that allows for electrons to shift around. Remember, we said that's why these have variable charges for your transition metals. So krypton, xenon, radon can bond. We're going to ignore them for right now. So based on this trend, francium has the least for your electronegativity. Fluorine has your most. So this one is asking me to put partial charges on each of the element in the following bonds. So I have to look at where they're at on the periodic table. Whichever one is more electronegative based on that trend, we are going to put the partial negative on it. Whichever one is less electronegative, we're going to put the partial positive. And so fluorine is the most electronegative element, so it is always going to be the one that's the greatest. So I'm going to do my little partial symbol. And this one's going to be partial negative. That makes chlorine automatically be partial positive. I'm going to do the same thing. I go look on the periodic table at where chlorine and carbon are. So chlorine is the closest to fluorine. Closer to fluorine means you're more electronegative. So it is going to be the more electronegative. Carbon is going to be less. So for this one, again, let me erase these so that you can see my next ones. So chlorine is going to be my partial negative. Carbon is going to be my partial positive. And then I have one last set to do. I have boron and chlorine. So again, if we look back at the periodic table, boron is here. Chlorine is there. Chlorine is going to be more electronegative because it's closer to fluorine. So in this case, boron is going to be my partial negative. Sorry, chlorine is going to be my partial negative. Boron is going to be my partial positive. This one says rank the following in order of increasing bond polarity. AP loves to have you rank things based on greater than, less than. If it says in order of increasing, for some reason people have trouble with increasing, decreasing. That means the one that is the most polar is going to be the last thing we list. We're going to list from least to greatest is increasing. So, oh, I have a typo on this one. So this is CLF, CCl, and this should be BCl. So on these, we want to think about which one is going to have the least electronegativity first. So if we look back here, boron is here, Cl's there, carbon's here, Cl's there, and then fluorine and chlorine. So the one that's going to have the least electronegativity polarity is going to be the one that is the furthest apart on this one. And so I'm going to write BCl first. Is less than. Next one I'm going to write is CCl is less than, and the one that is the greatest is CLF. AP makes you organize things a lot of times or recognize things based on greater than, less than symbols. Increasing means I'll list whichever one has the smallest to the greatest. There's also something called ionic character, and this means how likely a bond is to be ionic. Again, this is all based on electronegativity difference or how far apart they are on the periodic table. So for these, we're just going to look at where these different pairs are. This one's asking us which one is most ionic. So I have lithium and phosphorus. So if I go back here, I have lithium here, phosphorus here. So we know that it's ionic because it's a metal and a nonmetal, but they're pretty far apart. And then we have copper and sulfur. Copper's here, sulfur's here. They're really close, so that's probably not going to be the ones with the most ionic. They're probably going to be the least ionic. And then I have barium and oxygen. So barium is here and oxygen is there. And so we are trying to figure out which ones are going to be the most ionic or which ones are going to have the biggest difference in electronegativity, be the furthest apart on the periodic table. So lithium's here, phosphorus is here, copper's here, sulfur's here, and then oxygen here is barium is here. These are the furthest apart. So if we know that this is the least electronegative and this is the most electronegative, and these two things are about as far apart as they can be, lithium to fluorine would be the most, then these would be considered to have the greatest ionic character because they would have the largest electronegativity difference. And so which one is the most ionic? We're going to say barium and oxygen. It's all based on how far apart they are on the periodic table. And then our last little topic that we have to cover in this unit is determining metallic character. And this is just how likely is something to be metallic. It's again based on where it's at on the periodic table. If we know that the metals are over here and the non-metals over here, then this chart makes sense. The further I go up to this right is going to be more non-metallic character. The further down here to the left is going to be more metallic character. So we look at this. So aluminum is one of those weird metals. So aluminum is over here, and aluminum is a metal. But if you've ever used aluminum foil for baking or for using on the grill versus an iron skillet for baking or using on the grill, aluminum conducts heat and electricity pretty well because it is a metal. But since it's so close up here over next to these nonmetals, it does have some non-metallic properties. It conducts heat and electricity really well, but aluminum foil gets cool really, really quick. It does not retain that heat like your iron skillet does. So whenever I'm baking, I can touch the aluminum foil pretty quick, even if it's in the oven or on the grill, compared to I am never touching an iron skillet because it's going to burn me because it's retaining that heat because it has more metallic properties. So going down this way, these are the most metallic. These up here are the least metallic. So this one is saying just list 2 elements that have the most metallic character. You're going to choose anything that's down here in this corner. List 2 elements that have the least metallic character. We're going to choose anything up here in this top right corner. So for my most metallic character, I'm going to choose, let's say, rubidium. It's down there in that bottom left quadrant. And calcium. For my least metallic, I'm going to go with helium and oxygen. So it's just based on where those things are at. So when we're talking through this unit, all of this unit is going to fall back to this concept of electronegativity. So all the periodic trends are important, but electronegativity is by far the most important to be able to do types of chemical bonds.